Hello again and welcome guys to G Squared Academy, where excellence is as usual epitomized. So on the screen, as you can see there, what we're going to be looking at is atomic radius. So we're looking at the trend in atomic radius in the periodic table. And the radius of an atom, really, if we were to draw, let's say that's our atom, and that's the nucleus of the atom, and that of course is the shell, then the radius is going to be the distance there, that distance from the nucleus to the valence shell. And that's what we're looking at as the atomic radius. And all we're trying to find out here now is what is the trend in atomic radius in the periodic table, and how do you explain it so we can progress. This can be for CSEC classes, for CAPE, IB classes, etc., etc. Okay, so first of all, we will look at it in terms of going down a group, or we're going to go across the period. And across the period is always from left to right, really. So here's the trend. The atomic radius increases going down the group. And the reason for that is as you go down the group, you're adding an energy level to each of the subsequent species. And so therefore, you're adding the distance, or you're increasing the distance from the nucleus. So you're adding a shell, right, which increases the distance from the nucleus. That's just part of the answer. Another part of the answer would be that when you add shells, you're adding electrons to those shells. And those shells, of course, shield the nucleus from the valence electron. And because you're shielding the nucleus, you're decreasing the effective nuclear charge, which basically means that you're decreasing the strength of the nucleus as a magnet, if you can consider it a magnet, to pull electrons towards itself. So therefore, what happens is the radius increases. When you go across the period now, right, the atomic radius decreases. And why is that the case? Well, there are a number of reasons. One, you're adding, if we were to look at this period, for example, period 3, you're adding electrons one at a time and protons one going across. And you're adding all those electrons and protons to the same shell. The thing is, electrons are very light, they're negatively charged, yes. And you may say, okay, you're getting inter-electron repulsion. But the effect of adding an additional proton on the atomic radius is greater than that of adding an additional electron, because the proton is much bigger. And so therefore, what happens is, as you go across the period, the nuclear charge increases. And because you're adding electrons to the same shell, the pull of those electrons by the nucleus becomes greater as you move across the period. And so therefore, what you find is as you move across, the atomic radius tends to decrease because of an increase in the effective nuclear charge, which has to do with, of course, the lack of shielding and the increase in the number of protons in the nucleus of the atom. Okay, so this really explains the idea of atomic radius changing within the periodic table. In the next section, we're going to look at how the ionic radius of a species may change within the periodic table. Okay, guys, so in this section, what we're looking at is the ionic radius. And it could be said that the ionic radius changes similarly in the periodic table. It increases as you go down the group. Whoops. Let me get this color right thing here, right? So we're saying that it increases down the group and decreases across the period, right? Now, this can be a trend that you could look at, or you are expected to recognize based on the atomic radius because of the same factors which were mentioned previously about the change in atomic radius. Now, what the issue is generally is that looking at a neutral species, so looking at magnesium changing to magnesium ion. And the question is, how does the ionic radius vary from the atomic radius? Now, if you think about it, what happens is, and I'm going to write the electronic configuration for magnesium in a very simple way, 2, 8, 2, right? And this is 2, 8. Okay, so what happens now is that in the neutral species, you have 2A2, and the atomic radius is based on the valence shell being out here with 2 electrons. right? Now, when magnesium, the atom, loses these two valence electrons, it becomes 2,8. And what happens is that because you have removed electrons, pretty much, the magnesium becomes more positively charged. In other words, you now have two extra protons in the nucleus. Why do you have two extra? You didn't add two new protons. All that happened was that you lost two electrons. The two electrons would have nullified, in terms of charge, those two protons. But because you only remove two electrons and not touch the protons, you now have a more positive nucleus. The more positive nucleus is now able to pull those valence electrons closer to itself. Okay, and so therefore the ionic radius should be less in for cationic species, for cation positively charged species, should be less than that of the atomic radius. Okay, notice I mentioned that it is a positively charged ion, because now what we're going to look at are negatively charged species. So if I have nitrogen, for example, and the nitrogen were to gain 3 electrons to get a full outer shell, right? Now, what now happens is that the electronic configuration was 2,5 here, but now it's 2,8. So you have now added 3 electrons to the atomic structure. And in adding 3 electrons to the atomic structure, you have now decreased the effective nuclear charge, because you are basically adding electrons, which it was neutral previously, and now you have added electrons, and so therefore you have increased what we call the inter-electron repulsion. And because you have increased the inter-electron repulsion, the distance from the nucleus to the valence shell would increase. And this is for ionic species, negatively charged species. So generally speaking, the anion is larger in terms of radius than the neutral atom, in this case nitrogen. So the nitride ion would be larger in terms of radius than the nitrogen atom. Okay, and this is for anionic species. Now, what if somebody asked you to compare the radius of magnesium 2 plus to the nitride ion? Now, what you could say is that the magnesium ion is going to be smaller than the nitride ion. And why do you say that? The reason for that is when you add these 3 electrons to the nitrogen, you have increased inter-electron repulsion, and so therefore that causes the ion to become larger than the neutral atom. In the case of magnesium, you have removed 2 electrons and you have now increased the nuclear charge. And so therefore you are able to pull those valence electrons in closer. Notice here that both of them are 2,8, so they have the same number of shells. But the difference in ionic radius has to do with the effective nuclear charge on each of the two species. One losing electrons, having a greater effective nuclear charge. One gaining electrons, having a less effective nuclear charge. And that influences the size of the ion. I hope you guys find this helpful. I wish you all the best, and I'll see you next time.